Okay, hi everybody. So today we're going to talk about 5.3, which is called evaluating the definite integrals. And so this is a really nice section because last section in 5.1 and 5.2, we actually did this the long way, which is because we want to know where all these ideas are coming from. So in 5.1 and 5.2, our job was to find the area under the curve. And we did that by drawing rectangles that were very, very small. At first, we did them a little bit wider, but then after a while, we used Riemann sums and the definition of the definite integral to get that n value very large. So our rectangles are very, very small so we can get that area under the curve. But now we have something that's really nice, which is what's called the evaluation theorem. So I had mentioned before that your book didn't give you this notation, but I wanted to introduce it to you early on. And this is what's called the integral. And we did talk about this in 5.2, but now instead of drawing our rectangles and taking the limit as n goes to infinity of that Riemann sum, what we're going to do instead is if we have the integral for a continuous function f on an interval a to b, we would get the integral from a to b of f of x dx is equal to capital F of b minus f of a. And so recall that the capital F and the capital F of when we're talking about it in terms of a lowercase m, here we were talking about the antiderivative. And so what we're going to want to do here is that instead of doing it the long way, we're actually going to just say that, hey, instead of doing it that long way, just take the antiderivative and then plug in your bounds f of b minus f of a. And so this is what we're going to use to evaluate that integral. And we're going to do this by calculating that antiderivative. And this here is a capital F. So capital F here is referring to that antiderivative. And recall that you'd always check your antiderivative by saying, if I take the derivative of my capital F, am I going to get back lowercase f? So our original function inside that integral. So let's do a really quick example. This one's going to be very simple just so that you can get the idea of this process. So for example, let's say we wanted to evaluate the area under the curve of x squared from 0 to 1. Now, we did this the long way earlier in the chapter, but we also learned to be able to take the antiderivative. And so what I'm going to want you to do for now, just so that we can talk about this example in really good detail, is here, this is our f of x. So we know that f of x is equal to x squared. And now recall that in 4.7, we talked about that antiderivative. And so for the antiderivative, of f of x is I didn't want to do an equal sign, is capital F of x. And now recall that when we have something like this, when we have x to a power, to take that antiderivative, we have to add 1 to the exponent, because normally when we take the derivative, we subtract 1 from the exponent. So we'll add 1 to the exponent, and then we'll divide by that new power. So recall that if we have something like this, capital F of x is going to be x, and then we have that 2 plus 1, and then we're going to divide it by 2 plus 1, so by that new exponent. So instead of subtracting like we did with the derivative, we're going to add. So hopefully this is all coming back from 4.7. And so if we simplify this, we'll get x cubed over 3. And so this is our antiderivative, but recall that before I made you do a plus c because we didn't know what that constant varied by. For this problem, because we do have what's called a definite integral, we don't need to do that plus c just yet, and that's because we're going to use the bounds to evaluate this. So a definite integral is called a definite integral because we have bounds that we're looking at. We're observing it from A to B. And so whenever you're observing from A to B, you're finding an area under the curve for that specific bound. So you don't need to do that plus C because we have our bounds A to B, and we're actually going to use those bounds to evaluate. And so now that we have our capital F of X, this evaluation theorem says that the integral from 0 to 1 of x squared dx is equal to capital F of 1, so capital F of B, minus capital F of A. And well, my capital F is x cubed divided by 3, so that's actually going to be 1 over 3, 1 cubed, minus 1 over 3, 0 cubed. And so all I did here was I used my antiderivative and I plugged it into these values, f of 1 minus f of a. And that's how we're going to be evaluating that area under the curve, so we no longer have to use Riemann sums. And so if we simplify this, we'll get 1 over 3 minus 0, which is just 1 over 3. And so this is the area under the curve for 0 to 1 of x squared. And it's the exact same, it's the exact area under the curve. It's not an approximation, it's the exact value. So we don't need to write approximately, we'll be writing exact. Okay, so let's try one more just so we could get the hang of it. Another simple one, and then we'll do a little bit of a harder one after that. So let's do another one. I want you to evaluate the integral from 0 to 5 of e to the x dx. And like I mentioned before, the importance of you writing this dx is very important. Don't leave it out. It's super important that you leave it there because that tells us that we're doing it with respect to e to the x. Okay. And so for this, the first thing that we probably want to do is we want to find that antiderivative. So let's find that antiderivative. So our antiderivative is capital F of x, and this is our lowercase f of x. And remember that when we find the antiderivative, we're doing the opposite of a derivative. So for this one, we did the opposite of a derivative, and you are always welcome to check it by saying, okay, if I take the derivative of this, am I going to get back my inside function? And you do. So here, e to the x, we didn't really have a formula for it, or we did, and hopefully you memorized it for the exam, but if we want to take the antiderivative of this, sometimes it helps to think backwards and say, okay, if what value or what function is that I can write for my antiderivative, if I take a derivative of that, am I going to get back little f of x? And so remember that the derivative of e to the x is just e to the x. So the antiderivative of e to the x is just e to the x. And so like I mentioned before in 4.7, for right now, until we get into 5.4 or 5.5, we're not going to tackle anything onto here, onto the front of x, because that's going to require a backwards chain rule. So for now, we'll just keep it simple. And so this is our capital F of x, and we know that it's our capital F of x because if we take the derivative of e to the x, we'll still get e to the x. And so now we need to evaluate it. And so we know that the integral from 0 to 5 of e to the x dx is equal to f of 5 minus f of 0. So it's always b minus a. And I know that could be a little bit confusing, but it's always b minus a, okay? Because that's what our value says here. And so if we evaluate this, we'll just get e to the 5th power minus e to the 0 power, which is the same thing as e to the 5th power minus 1. And you are welcome to leave it like this. I don't need a decimal value for that on your exam. And so now let's do let's just do one more just to get some practice. And then we'll talk about the indefinite integral after this example. So let's do one more example. Okay, so now let's try a little bit more of a complex example. This one seems a little bit more complex only because on the previous examples, we only had one term in our integral. So we only had, for example, here we only had x squared. Here we only had, here we only had e to the x. But hopefully you remember doing this from 4.7, so it won't be too bad, but I just want to do it using the definite integral, which means that we have bounds at our integral. And so we're bounded by that. So now what we want to do first is, what I would recommend to do for these problems is to first rewrite them so that when you apply that backwards power rule or the integration power rule, you are easily able to do it. So the first thing that I would do is I would rewrite this as 1 to the 4th, 6, and now instead of writing the square root of x, I'll write x to the 1/2 power. And that way when I add 1 to that exponent, I can do it easily. And then I'm going to do minus 2x dx. And now remember that for our properties of integrals, we were able to separate these as well. So we can right now write the integral from 1 to 4 of 6x to the 1/2 dx minus the integral from 1 to 4 of minus the integral of 1 to 4 of 2x dx. You could do this and integrate each one separately, but you don't have to. In fact, what you can do is instead just integrate these on their own, but recognize that this is what's going on in the background, is you're integrating each term, or you're taking the antiderivative of each term separately. And so now what I want to do is if I take the integral, I'm going to erase this so that we just do it in one chunk. This is going to be my f of x term, right? And so my capital F is going to be the antiderivative of that inside. And so I'm going to actually introduce a newer notation here. So instead of writing capital F of x, I know that it's going to be f of x. I'm going to just take the antiderivative. And when I take the antiderivative, I'm going to do something different. So what I'm going to do is I'm going to write f of x. So if I take the antiderivative and I validate them at these spots here, that's the same thing as writing f of capital X. And then I'm going to do a big bar here. Let me do it a little bit lower. Actually, let me center this. So taking the antiderivative of that is the same thing as writing capital F of x from A to B. And so what I'm going to do now is I'm going to rewrite the antiderivative. So I'm going to go ahead and take that antiderivative over here. And so if I take the antiderivative, I'm going to get 6x, and then I can, and then we raise this up to 1, which will give me 3/2. And since I raised it up to 3/2, I now have to divide by the exponent, which means that we're multiplying by 2 over 3 in the front for that antiderivative. And then here I'm going to subtract 2, and I'm going to add 1 to this exponent over here. And so I'm going to get 2x squared divided by 2, because we divide by that new exponent. And I want to evaluate it from 1 to 4. And so this just means that I'm going to evaluate it, okay? And then I also want to point out, I don't think I did it earlier, is that once you take that antiderivative, we no longer need that integral sign anymore. So notice that from here to here, these were equal. All I did here was rewrite them so that I made my life a little bit easier. But once I take that antiderivative, I no longer need to write that integral sign. It doesn't make sense for you to write it because you already found that antiderivative. And so now what we're going to do is we're going to do that fundamental theorem of, we're going to do the evaluation theorem over here, and we're going to evaluate f of b minus f of a. Which means that we need to do, if we evaluate f of b minus f of a, and actually, I want to simplify that before I do that just because that'll make my life easier. This is going to end up being 2, and these are going to cancel out. So we're going to be left with 4 to the x, 4 times x to the 3/2 power minus x squared, 1 to 4. Okay. And now from here, what we need to do is now we're going to do f of b minus f of a. So we're going to do f of b minus f of a here. And so that's going to be 4. And then I'm going to rewrite this as the square root of x cubed. And so this is going to be the square root of 4. Actually, let's do a different color so that you guys can distinguish for what I'm actually doing. So it's going to be 4. And now I'm going to have the square root of x, but here I'm doing f of b minus f of a, so this is going to be 4 cubed. So all I'm doing here is I'm plugging in this value for b. And so now we're going to do minus x squared, and my x value here now is going to be 4 squared. Now I'm going to subtract f of a. And so f of a is going to be 4 times the square root of 1 cubed minus 1 squared. Okay, perfect. And now I want you to notice that this term here is f of b minus, and then this is going to be my f of a. So all we're doing here is applying that that evaluation theorem here in order to evaluate this integral, okay? I'm just showing you footnote here, which is very commonly used, and you will use it later on as well. You'll use it a lot in calc too. Okay, and so now from here, we're going to evaluate this. This right here, this 4 times 4 cubed is going to give me 32 minus, and then 4 squared, that's 16. And then minus, and then this is going to give me 4 times 1 cubed, which is just 4 minus 1, which is 3. And so here, this actually comes out to be positive 13. Okay, and so that's our answer. So this is different notation here, and you'll get used to it the more and more you use it, just like you'll get used to, you got used to that derivative notation, you'll get used to the integral notation and the bounds here. This means that you're going to evaluate it, but you haven't yet, okay? And so the next thing we're going to talk about is the difference between a definite integral and an indefinite integral, and how we notate each of them, and what we need to do for each of them, because although it seems like the same process for a definite integral and an indefinite integral, there is a slight difference between those two, and actually we'll write that down in the next page over.